So I want to thank the organizers for inviting me to speak about their own work. This is joint work with Iftach, Eran, who's here, Kobi Nissim, and Jad, who's here. And it's going to be about a dichotomy theorem for key agreement. So let me try to tell you what we're going to study. So I'm going to be interested in two-party protocols between two polynomial time parties, where the parties don't have private inputs. They have a common input, which is a security parameter, but they don't have private inputs. The parties interact via this protocol. And then at the end, each party receives the transcript, and each party also receives an input. The input of the first party is 1 bit. It's called X. And the input of the second party is 1 bit. The output of the second party is 1 bit. It's called Y, right? I'm interested in protocols, right, where the outputs are single bits. So here is an example of such a protocol, a key agreement protocol, which we all know and like. A key agreement protocol is a protocol that satisfies agreement, namely the two outputs are identical with probability close to 1, and secrecy, saying that every probabilistic polynomial time eavesdropper machine, E, that gets to look only at the transcript and, say, tries to predict the key of the first player, right, cannot do it with probability significantly larger than half. And here is what I want to study. If I were to ask such an eavesdropper, probabilistic polynomial time machine, right, from your point of view, what do you think, how do you think that X and Y are distributed, conditioned on the transcript that you saw? Then this machine will say something like that. Look, the first input, the input X, is distributed like a random coin because I can't predict it. And the second output Y is distributed like X. So from my point of view, I believe that the probability space is a probability space of sampling a random coin and producing it twice. X and Y are just two completely correlated random coins. But of course, that's not true, right? There are no setup assumptions here. So information theoretically, for every transcript T, if I were to take a look at X and Y conditioned on T, what I see is a product distribution. These two variables are completely uncorrelated, right? So this phenomena, right, where things are uncorrelated, but the computational time machine seems to think that they're correlated, is something that I would like to refer to as computational correlation, right? So that's what we want to study. Okay. So a key agreement protocol is a protocol that is interesting in the sense, right, that a computational correlation emerges. And now let me give you an example of an uninteresting protocol where computational correlation does not emerge. So, and it's a lot of fun to do examples of uninteresting protocols, right? So here is an uninteresting protocol. The two parties don't interact, right? Instead, in order to produce their outputs, so the two parties have numbers, PA and PB, between 0 and 1. And in order to produce the output, party A samples X according to UPA. So I'm going to use this notation UP to denote sampling a coin which has bias P. So A samples X, his output, according to UPA. B samples B according to UPB. And of course, as you can see, X and Y are uncorrelated. So this is an example of an uninteresting protocol. Let me give you another example of an uninteresting protocol. So UPA is the distribution of a coin which is one with probability PA. Okay? So here is a slightly more interesting, but still uninteresting protocol. This is a protocol in which A and B do interact, right? But then at the end, in order to produce their outputs, they engage in the following thing. Right? Each of them has a polynomial time computable function. A has PA and B has PB, which, given the transcript, produces a number between 0 and 1. And in order to produce the outputs, A implies PA. Okay, so I was giving an example of a slightly more interesting protocol. So in this protocol, the parties do interact, right? But at the end of a protocol, each party, in order to select the output, has a polynomial time computable function, which given the transcript, tells him what is the bias of a coin which he wants to toss. So there are two polynomial time functions, PA of t and PB of t, and then the player A, in order to sample its output, it samples X according to U PA of t, and B samples B according to UPB of t, right? So this is an example of a protocol. Now here, right, I mean, the two outputs are correlated, right? I mean, like X and Y are correlated via t, but I claim that in such a protocol, there's no interesting computation correlation. Well, why is that? Because if you are a probabilistic polynomial time eavesdropper that only takes a look at the transcript, then since PA and PB are polynomial computable functions, then you can compute PA of t and PB of t by yourself, and then you have complete understanding of how the probability space of X and Y conditioned on t looks like. Therefore, right, there's no hidden computational correlation, and for example, a more formal statement that I could say is that such protocols cannot yield a key agreement. Right? So the formal way of saying this would be that if you had a key agreement by such a protocol, then, right, I mean, the key agreement is not coming from the protocol. So I want to capture this notion of an uninteresting protocol. So I'm going to give a definition of right, I mean, like a definition of all uninteresting protocols. So I'll say that a protocol pi is uncorrelated if there exists a polynomial time machine, which I call a decorrelator, which, when given input, the transcript, you run the protocol, you apply the decorrelator on the transcript, it gives you two numbers, PA and PB, such that if you were to sample independently X prime according to UPA and Y prime according to UPB, and you were to compare the real experiment, X, Y, and T, with the simulated experiment, X prime, Y prime, and T, then these two experiments are computationally indistinguishable. The real experiment, in which the outputs are chosen as they are by the protocol, is indistinguishable from the experiment where the outputs were chosen by the decorrelator. Okay? And I'm going to call this an uncorrelated protocol. So, and the point I want to make is that X prime, Y prime, and T are uninteresting from a cryptographic viewpoint. For example, such protocols cannot be transformed into key agreement protocols. Now, in order to make this statement more formal, the way I should say it is that if you had a transformation that was transforming such a protocol into a key agreement protocol, then I can take your transformation, use it without access to the protocol, and get a key agreement out of this. So that's a formal meaning of what I'm saying there. But the point that I want you to think about is that, right, this is an example, this is the way completely uninteresting protocols look like. So now I'm ready to state the result, the dichotomy theorem for key agreement. So the result is saying something like that, right? There are key agreement protocols, right? These are very interesting computational correlation emerges. And then there are uncorrelated protocols. These are trivial protocols, no computational correlation emerges. And we can ask ourselves, is there anything in between, right? What kind of animals do we have in between? And the theorem is saying that modulo some caveats and technicalities, that I'm going to explain later on, right? For every polynomial time two-party protocol, either it is uncorrelated, either it is completely uninteresting, or it can be transformed into a key agreement. You can get a key agreement out of it. And the way we interpret this is that, right, I mean, it's a dichotomy, there's no intermediate concept, and there's no interesting concept in between. Either, right, you're uncorrelated, or if you're slightly correlated, I can get a key agreement out of you. Okay? So why do we think, yeah?
Maybe just a question about the notion of decorrelator.
Sure.
So what does it mean that the decorrelator produces P and PB based on the transcript?
So the decorrelator is a polynomial time machine which given the transcript, right, just outputs these two numbers.
But then you're comparing like the two examples where you have x, y, and the transcript itself. But
So I'm comparing two experiments. In one experiment, the real experiment, I ran the protocol, and the protocol produced x, y, and t. And then I'm comparing this to a simulated experiment where I ran the protocol, I only took t from this protocol, I ignored x and y, and then I produced x prime and y prime in a way so that they are independent just by the way I did it, right? I sampled x prime and y prime independently conditioned on t. So I'm comparing these two experiments. In the second experiment, right, I mean, like, everybody knows the numbers PA and PB if you see t, and I want to show, right, I'm saying that the protocol is uninteresting if these two experiments are indistinguishable.
do you ever use the fact that the correlator can output different P and PB for different transcripts?
Of course, right? I mean, like this is the difference between the first example of a completely uninteresting protocol where PA and PB are constants, and the second example where PA and PB can depend on T. Okay? So, yeah.
So also, why do you partition the thing into two stages? Why won't you
Because yeah, so I could, right, I mean, like, I'll be talking about like a combined notion which is called the simulator, right, a bit later.
We can think about the
Yeah.
that just produces.
Yeah, but the way we're going to prove it somehow, right, is easier to explain like this. So you can think about it as like a big machine, which is a simulator, which given t simulates x prime, y prime, and t.
The correlator is deterministic?
That's a good point. So at this point, let's think about the decorrelator as deterministic, but I'm going to make it randomized in a moment. Okay? So why is this interesting? So Iftach alluded to this in his introduction. So here I wrote our theorem, and here on the other side, I wrote the celebrated theorem of Impagliazzo and Luby that distributional one-way functions imply one-way functions. And very subtly, I'm trying to make you think that these two theorems are somewhat alike. I'm not sure whether everybody notices that, but hopefully some people will. And so let's read and compare. So I'm going to state Impagliazzo and Luby in the following way. Right? For every polynomial time procedure P which gets input x and outputs t, then either P can be reversed, namely that given an output t, you can sample a uniform x conditioned on P of x equals t. Right? So you can reverse the computation P. But if you can't reverse the computation P, then Impagliazzo and Luby say that they can give you a one-way function. Right? So either every a procedure is trivial, it can be reversed, or it implies a one-way function. And the point I'm trying to make is that this is sort of a two-party analog of Impagliazzo and Luby. For every protocol, either it is completely trivial, completely uninteresting, or you can get a key agreement out of it. Okay? Yeah?
Just to make things more complicated, you have to say infinitely often or infinitely often.
I just said that there are caveats in the theorem, and there are going to be infinitely often, right?
It's also in the like.
Okay, so again, continuing this subtle comparison to Impagliazzo and Luby, why do we like Impagliazzo and Luby? So we like Impagliazzo and Luby for at least two reasons. One, it's a clear dichotomy, right? I mean, there's no intermediate concept. Either a computation can be reversed, or you can get a one-way function, right? So it's very nice to have a dichotomy. The second reason is a methodological reason, which Iftach mentioned, saying that once we have this tool of Impagliazzo and Luby, in order to show that a certain primitive implies one-way function, which we interpret as a lower bound, but you can't construct the primitive without a one-way function, you only have to show that this primitive cannot be reversed. Right? So this gives you a methodology to show that certain primitives imply one-way functions. And I would like to argue that our theorem is the same in the sense that if you want to show that a certain protocol implies a key agreement, it's sufficient to show that the protocol is uncorrelated. right? Or the way I want to, right, if you want to go out of a talk and, say, people ask you, what happened, then Impagliazzo and Luby said that in order to show that you live in mini-crypt, in Russell's mini-crypt, right, it's enough to show that the primitive cannot be reversed. We show that in order to show that you live in cryptomania, it's enough to show that the protocol is uncorrelated, okay? So we have some applications, right? We have some applications. So in the paper, we had an application showing that using this technique, we can show that two-party differentially private computation of the XOR function for certain parameters imply a key agreement, which was not known before. And I'm actually just a sideshow for Nikos, who's going to show a result, an application to a non-trivial constant round, a coin flipping protocol. Let me just mention that since we studied differentially private computation, we have a follow-up work where we improve the result. The lower bound becomes stronger. This is joined with Yiftach, Noam Mazor, who is here, and Jad, who is here.
How is this related to the completeness results for OT? So the secure computation of the non-trivial function?
So I know very little about OT, but I'm not sure whether that's related, right? Like, the way I see, from my perspective, right, I mean, you have one-way functions, key agreement, oblivious transfer. And, right, I mean, this is only, you're talking about what? About the
first one.
The first application. So in this work, we're only able to show that a differentially private computation implies key agreement, and in follow-up work, we show that it implies oblivious transfer.
So this result show which levels on the concept about which function. There is a dichotomy also there. So how is it related?
No, so I mean, for OT, we don't have a dichotomy. This is one of the open problems. I'm only going to talk about key agreement.
This is for the information theory itself. This is for computation.
Okay.
Okay, so now, right, let me present the dichotomy theorem with all the caveats. So this is what I said before. For every protocol pi, either it is uncorrelated or it can be transformed into a key agreement. And let me start adding the caveats. First of all, for Amos, I'm going to add infinitely often, right? So I'm going to add two infinitely often. For every protocol, either it is uncorrelated on infinitely many choices of the security parameters, or it can be transformed into a key agreement on infinitely many choices of the security parameters. Now, infinitely often should appear here, right? Because it could be the case that the protocol is a key agreement on input, on even input lengths, and a completely trivial protocol on odd input lengths. But I'm doing things not in the right way. There should have been one infinitely often, and you should be able to choose where you want to put it, whether you want to put it here or here. I'm not able to show that. I have two infinitely offends, and you don't get to choose anything. Okay? So that's the first caveat.
So per input length, you don't have...
No. The second caveat is that, in fact, I'm going to do a quantitative definition of what is uncorrelated. So I'm saying either a protocol is row uncorrelated. What do I mean by a row uncorrelated protocol? So instead of talking about computational indistinguishability with negligible distinguishing advantage, I'm going to talk about computational indistinguishability with distinguishing advantage row. So two ensembles are computationally indistinguishable with distinguishing advantage row if no probabilistic polynomial time machine can distinguish them with probability larger than row, right? I mean, the distinguishing difference should be smaller than a row. And then the question is, what row can I get? Do I get a negligible row? And the answer is no. The theorem says either for every constant row larger than 0, pi is row uncorrelated, or it can be transformed into a key agreement. So I don't get to do row which is polynomially small or negligible, only a constant. That's a major caveat. But still, right, I mean, in order for you not to run away from this talk, there are applications, right? So it might be meaningful. Yeah?
You don't know how to work over larger alphabets? Like, it's right, I'm guessing.
I mean, we would first need to solve this problem for bits, and then we would start talking about larger alphabets.
So if you would put differently, if you would want to walk over a longer
Yeah, I mean, you can probably reduce, yeah.
exponential developing the complexity.
Yeah, I mean, one way, yeah, I mean, that's, right, these two things are related, right? You're going to see it in the proof. Okay, and finally, for tal, right, I mean, this is not a caveat, this is a technicality. The decorrelator, I'm going to allow the decorrelator to be randomized, but if I'm allowing the decorrelator to be randomized, if I think about it as a deterministic algorithm that gets random coins R, then in order for things to mean what I think they mean, I need to add R to the two experiments, right? So it should be the case that the two experiments are indistinguishable even when you see R, in order for the intuition of what is an uncorrelated protocol to be maintained. Okay? Don't worry about that. That's not a caveat. That's the way things should be.
So if the decorrelator chooses probability half to set P8, PB to be 0, probability half to set
Then it creates correlation, right? So in order to avoid that, I'm adding R over here. Okay? That's once then I get rid of all these like bad behaviors, right? So like the decorrelator can't put pineapple over pizza or whatever is a bad behavior these days. Okay, so that's the main theorem, right? With all the caveats and technicalities. And now let me tell you what's the machinery that goes into proving it. And in order to do that, I'm going to define something that I'll call a forecaster, which is going to be very related to a decorrelator, but slightly more general. So what is a forecaster? A forecaster, F, is a probabilistic polynomial time machine, which when you give it the transcript, and it needs to tell you what it thinks is the probability distributions of x and y conditioned on t. Right? Now, since x and y are bits, this is a probability distribution on only 2 bits, it is completely determined by 3 numbers. What are the numbers? So the forecaster should tell you, I think that the probability that x is 1 conditioned on the transcript is something, PA. I think that the probability that y is 1 conditioned on the transcript and on x being 0 is something. And I think that the probability that y equals 1 conditioned on the transcript and on x being 1 is something. So this completely describes, right? The details are unimportant. The point is that the forecaster needs to output 3 numbers, which are a forecast for what it thinks is the probability space of x and y conditioned on t. How do we measure the quality of a forecaster? So I'll say that the forecaster is a row forecaster. It's good up to row for a protocol pi if the following holds. If you were to run the protocol and then apply the forecaster on the transcript to get the description of a probability space, and then you were to sample x prime and y prime according to this description. Now note, x prime and y prime can be correlated, right? I mean, this definition allows x prime and y prime to be correlated. Then it should be the case that the real experiment and the simulated experiment are computationally indistinguishable up to row. Okay? So, said differently, a decorrelator is a special case of a forecaster where the decorrelator is a forecaster that forecasts that the probability space for every t is uncorrelated. The x and y are independent, right?
Rho is a constant here?
Yeah. In the theorem, but I'm going to state in a moment, rho is going to be a constant.
But then, I mean, you fix a constant, but the running time of the attacker is undefined polynomial, which could kind of...
Yeah, I know where you're headed, and I'm going to talk about that.
So, Ronen, are there unforecastable protocols? Like, is that
No, so I'm going to show the next theorem that I'm going to show. So here's the definition of a forecaster. Here's the picture. I'm going to show, right, that for every protocol and for every constant row larger than 0, there is a polynomial time row forecaster. So that's the main theorem, right? So you can always forecast up to row, okay? And once again, these come with the two usual caveats, computational indistinguishability up to rho, and they are infinitely often. So you can forecast, the forecast is this indistinguishability only holds on infinitely many input lengths. Okay?
How does the complexity of the forecaster depend on rho? Does it go in the exponent of the Ronen time?
I don't know how it depends on rho.
Nobody knows.
Nobody knows. You're going to see, right? If you know, tell me, but I don't know. So I'm going to try and answer Yevgeny's question before he asks it, right? Because I have a feeling that Yevgeny is going to say something like, just to make sure that I understand, can I? Right? So Yevgeny, you do understand, and here is the answer. So for the sake of perspective, I want to compare this result about forecasters to something that is called the leakage simulation lemma, which is extensively studied in cryptography. So the leakage simulation lemma talks about a very similar scenario. So in the leakage simulation lemma, there are two random variables. T is a long random variable over m bits, and z is a short random variable, let's say over a constant number of bits. And the leakage simulation lemma asks something like this. Suppose we're running limited complexity, and we're only given t. Can we simulate a random variable z prime such that the pair zt is computationally indistinguishable than z prime t? Right? And I want to tell, right, I mean, this is exactly the same kind of thing that I'm interested in the case where z is the pair x and y, right, which is short, it is 2 bits. So this is exactly the same kind of notion. Forecasters are exactly the same kind of notions that come up in the leakage simulation lemma. But there are some differences. So let me try and point them out. So in order to point them out, let me restate our result about forecasters in a setting which is more similar to the leakage simulation lemma. So the result says something like that. We say something like that. For every constant rho larger than 0, there exists a probabilistic polynomial time simulator. Now I'm calling the forecaster a simulator, like Benny wanted, right? This simulator runs in fixed polynomial time. Let's say time n to the 10. Such that if I were to sample z prime, right, by applying the simulator on t, then no probabilistic polynomial time machine, even ones which large in much higher time, in time n to the 100, can distinguish zt from z prime and t, and I have this caveat, the infinitely often, right? So here is the first caveat, infinitely often. Here is the second caveat, that rho has to be a constant. Now, what does the leakage simulation lemma say? It says something very similar in spirit. It says that for every rho, not necessarily constant, right? Then I want to have a simulator. But the leakage simulation lemma, right, in the order of quantifiers is different. It says, you know, tell me what is the complexity of the distinguishers that you want to work against. Here, complexity will be measured by circuit size. So tell me the size S of the distinguishers you're interested in. And then there exists a simulator, a circuit, but it's a circuit of larger complexity than the distinguisher, of size S prime, which is larger than S. So we know exactly how large it should be, larger than S, such that if I were to sample Z prime using this simulator, then no circuit of size S can distinguish ZT from Z prime T. Okay? So let's stare at this for a moment. There are 3 key differences. The first difference that everybody sees immediately is that here we're talking about the uniform world, probabilistic polynomial time machines, and here we're talking about circuits. That's immaterial, right? Because there are like more uniform versions of the leakage simulation lemma. That's not the key difference, okay? Yeah, but I'm not going to talk about it. The second and more important difference in my mind is that in our result, right, we have a simulator that runs in some fixed complexity and it is able to work against distinguishers which run in much larger complexity, whereas here, you should tell me what is the complexity of the distinguishers, and then the simulator runs in larger time than in larger complexity than the distinguishers, right? So that's the key difference, but we pay a price for that, right? We can only do it for constant rho, and we have these infinitely often, okay?
So you do something when functions exist, you do something else when functions don't exist.
What?
Like you do something when functions exist, you do something else when functions don't exist.
Let's see. Okay, so now, right, I mean, here is the theorem, and I want to tell you something about the proof, right? The theorem says that for every rho larger than 0, and for every protocol, there exists a rho forecaster for pi. And here is how we prove it. So the way to think about it is that, right, I mean, we want to select a good forecaster. So we arrange a competition between all possible forecasters, all probabilistic polynomial time machines, okay? And for each one of them, we assign a price, right? I mean, how good are you doing in forecasting the distribution that you need to forecast? So we have some price function saying, if you're a forecaster, what is the price that I associate with you? The price function is written over here only for you to be impressed, right? I'm not going to talk about it at all. Please ignore it, okay? And then I'm going to say something like this. No matter what is the price function, just the fact that it lies in some fixed interval, for every such price function, I'm going to define a forecaster to be mu optimal if the following holds. If there exists an infinite subset of inputs, such that my forecaster is on these inputs has price which is not much worse than any other forecaster, right? So I'm going to say that a forecaster is mu optimal if it is allowed to choose an infinite subset of inputs on which it wants to play, such that for every other probabilistic polynomial time forecaster, for every sufficiently large input, right, the price that I'm getting is not much worse than the price that the other forecaster is getting, okay? And this definition is carefully tailored so that you can prove the following theorem. For every mu larger than 0, for every constant mu, there exists a mu optimal forecaster. Well, why is that? Well, you take one machine. Either it is already optimal, or if it is not optimal, right, then there is some other machine that does significantly better on infinitely many input lengths. So let's take that machine. But maybe it is also not optimal, right? So we'll take another machine. But this process has to converge. Why? Because mu is a constant, and the price function lies in a fixed interval. Right after a constant number of iterations, this process has to converge. Therefore, there has to exist an optimal forecaster, but I don't know in what time it runs, right? I mean, it's a polynomial time machine, but I have no idea what is the polynomial time. Right? For every mu, there is a mu optimal forecaster.
Is it the only reason you need it to be constant? Or?
That's the only reason I need it. I mean, like, there are other places where, right, I mean, where we would have difficulties if it wasn't a constant, but I don't think these are real difficulties. And then the main technical thing is to use this specific structure of a price function to say that for every forecaster, if there exists a probabilistic polynomial time distinguisher, which distinguishes with distinguishing advantage rho, then I can take the polynomial time forecaster and the polynomial time distinguisher and use them to construct a better forecaster where the price is significantly reduced. It doesn't matter that here I have rho squared and not rho, just some function of rho. So this is saying that if I took an optimal forecaster, right, up to, say, rho squared, and if some distinguisher was able to distinguish with large probability, right, then I could take my forecaster and improve it. But I know that this is impossible, right? Therefore, my forecaster produces a distribution which is indistinguishable from the real experiment. Okay? So if I prove this claim, I prove the theorem. Okay?
So the existence of the optimal, finding this optimal forecaster is not efficient, right?
No, I just show that it exists, right? I mean, like this iterative argument only shows existence, and I have no idea which machine it is and in what time it runs, right? But it runs in polynomial time. So now there are two things. How much time do I have? As much as I like. So there are two things that I want to show you if I have time. One is I want to show you that once you have forecasters, right, you can prove the dichotomy theorem. And the other is, I want to say something about, how did we choose the price function and how does it work? Okay? So let me start by showing you that forecasters give the dichotomy theorem. So here is the intuition. So if there are two cases. Yeah. 5 minutes? Okay. If except, right, if for all t, or except for very few t, the forecast of a forecaster is that x and y are independent, are uncorrelated, then the forecaster is already a decorrelator, and I win, right? So if a forecaster forecasts that the two variables are independent, right, it's already a decorrelator, so I need to prove that either there exists a decorrelator or there is a key agreement, so there exists a decorrelator, I win. So the interesting part is to show that if for many t's, for a noticeable set of t's, right, the decorrelator thinks that x and y are correlated, right, then I promised that I'm going to construct a key agreement. Yeah. So how will I be able to do that? So here is the approach. So the main advantage of the simulated distribution over the real distribution is that in the simulated distribution, x prime and y prime have real information theoretic uncertainty conditioned on t. Right? I mean, it could be the case that in the real distribution, x and y are completely determined by t, right? Right. So once you know t, if you're unbounded, you completely know x and y, but it's only because you're polynomial time, right, that you don't understand this. Whereas in the simulated distribution, right, just by construction, x prime and y prime have real information theoretic uncertainty conditioned on t. That's the way I sampled them. Okay? So this means that in order to construct a key agreement protocol, it is sufficient for me to forget about x, y, and t, about the real experiment, and focus on the simulated experiment. And now I need to construct a key agreement in an information theoretic setting. That's much easier, right? And once I'll do that, because of the indistinguishability, if I construct a key agreement on x prime, y prime, and t, it will be a key agreement on x, y, and t up to this loss of rho. Lucky for me, key agreement can be amplified, right? So the fact that I lose this rho both in the secrecy and in the agreement, right? As long as this loss is such that there's still distance between secrecy and agreement, I will be able to amplify and win. So, right? So my task now becomes, let's construct a key agreement in the information theoretic setting on the simulated distribution. So let's do a key agreement in the information theoretic world. How does the information theoretic world works? In the information theoretic world, there are no protocols, right? There's a dealer, and the dealer gives the input to each party, right? So a party A gets the output x prime, right? The simulated x prime. Party B gets the output y prime, and both gets to see the transcript, right? And now I need to show how to construct a key agreement in this realm. And one thing that I'm going to do, which is strange when you think about it, is that when I construct the key agreement, I'm going to use the fact that the parties A and B can run the forecaster. It's a polynomial time machine. So now, not only do I not know the running time of a forecaster, I don't know the running time of the parties in my key agreement protocols. I just know that it exists, right? I'm going to use the forecaster. And the protocol that I'm going to do is something that I'll call the one-sided von Neumann protocol. And it works like this. So party A runs the forecaster to compute it. It looks at T and it computes PA, right? How is X prime distributed conditioned on T? And then it samples another independent output, X double prime, from the same distribution. So now X prime and X double prime are two independent random coins with the same bias. Okay? And now we run the von Neumann extractor. So what does this mean? So A informs B whether X prime is equal to X double prime, whether the two coins are the same. And if they are the same, both parties abort. They didn't succeed in doing the key agreement. But if they are different, if X prime is different than X double prime, then they continue and each of them output its output. Now, why should this work, right? This should work because think of, from the point of view of the adversary, right, the unbounded adversary in this realm, X prime and X double prime are two random coins which have the same bias. So conditioned on X prime different than X double prime, X prime is a completely random coin. That's the whole trick of a von Neumann extractor, that the probability of 0, 1 is equal to the probability of 1, 0, right? And that means that we have perfect secrecy, right? I mean, the adversary doesn't know anything about X prime. So secrecy follows from the von Neumann extractor. Now, what about agreement? Because the forecaster thought that X prime and Y prime are correlated, that X and Y are correlated, X prime and Y prime are really correlated. And that means that some of its correlation survives even when I conditioned on X prime equals to X double prime, and this correlation is kind of like agreement. Now you have to do something more because correlation can be agreement or anti-agreement, but you can know whether it is agreement or anti-agreement because the other party can also run the forecaster and know whether this is agreement or anti-agreement, what the probability space looks like. So I get a perfect secrecy and somewhat agreement. I can amplify that to a full-fledged key agreement, right? So that's the protocol. And once I do that on the original probability space, I get a construction against polynomial time adversaries. So I don't have time to speak about the price function, right? Or should I? No. So let me conclude. So first of all, it's been fun with all the computer trouble. I didn't get to sing, but right, that's not too bad. So here is the theorem. For every polynomial time two-party protocol, either pi is uncorrelated or pi implies the existence of a key agreement protocol. And interesting open problems are, first of all, can we remove the caveats, right? Can we get negligible distinguishing probability and have only one infinitely often wherever we wanted to? It looks very difficult because, right, we were using a lot of like cheats in order for this to go through. Nikos is going to show an application of a dichotomy theorem, but it would be great if other people would come with more application of a dichotomy theorem. And finally, following what Alon asked, right, can we give such a classification for oblivious transfer protocols? But for, right, like, right, like we want to have some classification saying for every protocol, either it is trivial in the sense that it's clear there's no oblivious transfer here, or it can be transformed into oblivious transfer. So we tried that a little bit, and the only thing that I can report is that it doesn't seem that just copying these techniques as are works, but who knows, okay?
I just have a comment. We have an old paper with Omer, Rani Harnik, and Moni on the indexing the computational setting, on completeness of OT. There is a dichotomy there.
But there's
Not efficient.
no,
It's a property of the function, it's called computational or non-positivity, and it implies completeness.
but it's not a dichotomy in the sense that if it doesn't have a property, then it's trivial in the strongest sense.
It is in some weak sense with some caveats, like infinitely often, and you don't get to choose them.
No, so I mean, there can be many, right? Like the point here is methodological, right? I mean, we would like to come up with a dichotomy, right? Like everybody, right? A dichotomy theorem should be measured by whether it is useful, right? So you can always say a dichotomy theorem is every protocol is either an OT or not an OT. That's a dichotomy. That's great. But what you want is you want to say something like, I want the dichotomy to be useful in the sense, but I can use it as a tool to show that certain protocols imply oblivious transfer. So there's room for a lot of different dichotomy theorems from all sizes and colors.
Just to make sure I understand. Well, is there some kind of, can you state like even, famous theory of like Aldrich-Levin, initially they stated in this weird asymptotic terms, but then people state precise, like T epsilon implies T, T prime, whatever.
No, I can't.
State the precise is a...
I have no idea, because you saw my proof technique. You saw my proof technique. I have no idea, right, what's the running time of a protocol that I'm constructing. I'm using the forecaster, which was found by a non-constructive argument, which only shows that it exists, and I have no idea in what time it runs or how it depends.
You should be able to state something, say, either there exists like a decorrelator that runs in time T prime, or there exists key agreement secure against guys who run in time.
I didn't try that, but yeah, I could try, yeah.
It's an amazing qualitative, but I think it would be interesting.
So can you relate the complexity of the forecaster to Levin's universal argument, like for one-way functions?
Even though I was presenting it in the realm of Turing machines, the argument is not an enumeration, right? It would work even if a family of forecasters wasn't countable, right? So it's not exactly right. So and I could try doing things like that, right? But let me just say, my personal preference is not to use these kind of cheats. So I'm disappointed that we had to use these kind of cheats here. I don't like them. Right? That's just a personal preference.
The adversary against the key agreement protocol has it's only against uniform adversaries, right?
What?
The security of the key agreement protocol is only against some kind of uniform adversary.
Right. But the reason this comes up, because I want to use the forecaster inside my protocol, if I wanted to get a dichotomy theorem against non-uniform machines, then since I want to run the forecaster in my protocol, the protocol that I would end up constructing would not be uniform. So the reason I'm stating this for uniform is because everybody likes their final protocols to be uniform, but there's nothing inherent about this technique only working for uniform machines. If you were allowing me to construct a key agreement protocols where parties are circuits, right, this would still work. Right? You just change, every time you write probabilistic polynomial time machine, write a polynomial size circuit.